Alright guys, this is the first problem that we're going to do here. Pretty easy problem, but I just want us to get a feel for what's going on here, okay? So let's look at it. Consider a hydrogen atom and a perturbation of the hydrogen Hamiltonian, H naught. And just if you were curious, the hydrogen atom, oopsie doopsie, the the unperturbed Hamiltonian, H naught, is, if I remember correctly, it's p squared, right, over 2m. Yeah, it's just the regular one, except that the potential is going to be a squared over r. It's potential energy. Okay, this is the electrostatic potential energy, but that's not important. It was just pretty cool that I just wanted to mention it. Anyways, we perturb a delta H, and delta H is a delta function, okay? Delta of r, and r in this case is going to be the r vector, three-dimensional. And I guess these constants are just to make the dimensions work out. Okay, so here alpha is fine structure constant. In fact, alpha is equal to 1 over 137 approximately. And A naught is the Bohr radius. Okay, find the first order correction. Okay, simple enough. Now, if you guys remember from the previous video, the first order energy correction was, we had a formula for it, and we derived it to be delta H and N, right? And we said that this was defined to be, this was our shorthand notation for N0, delta H, N0. Okay. So first of all, which state do we want to find the correction to? And it says here that we want to find the correction to the ground state, right? The ground state energy correction. Okay? So the ground state energy, let's write it as 0, 0. And what this means is this is the ground state, and this is the unperturbed ground state. Okay? Alright, so now let's plug this in. So we have 0, and then delta H is going to be this term right here, pi over 2, and then alpha to the 4th, mc squared, a naught cubed, delta of r, and 0, 0. Okay, we can factor out these constants, right? They're just constants after all. So this is equal to pi over 2, alpha to the 4th, mc squared, a naught cubed, and then the matrix element of the delta function. Okay, and if you remember from an analysis of the hydrogen atom, the ground state is actually represented, well, if we look at the position representation, which would be like this is actually the wave function, right? The ground state wave function. I'll just write ground state for now. And if you remember, in the hydrogen atom, we label states by N, L, and M. This is the principal quantum number. This is the angular momentum quantum number. Angular momentum. Remember, these are eigenstates of, so for, just quickly to recap, for hydrogen atom, our whole purpose when we're deriving the eigenfunctions of the hydrogen atom, we said that L would be the angular momentum quantum number, which would be an eigenstate of L squared. Remember, we had L squared times Lm equals h bar squared L plus 1 times Lm. If this doesn't make any sense to you, then just educate yourself in regards to angular momentum, spherical harmonics, things like that, because I assume you guys know it at this point. And then M is the magnetic quantum number, or also, let's write magnetic quantum number. And it's basically the Z component of angular momentum, right? If we have this, then this is equal to, it's just h bar times M. Okay? This is the familiar angular momentum algebra. I'm not going to get into this. I just wanted to tell you. So the ground state is written as 1, 0, 0. So n equals 1, L equals 0, M equals 0, right? And this is a function of R. And in fact, if you look this up, it's going to be some normalization constant, call it n, and then we're going to have the radial wave function 1, 0, and this is a function of R, and then we're going to have the spherical harmonic y 0, 0 of theta and phi. Okay, and I saved you the time. This is just equal to radical pi a naught cubed. That's our normalization. Times, this guy is going to be e to the negative r over a naught. And then the spherical harmonic is absorbed into this. Okay. So what we have to do now is plug this into our perturbation, first order energy correction equation. And what we get is that En1 is equal to, okay, well, we're going to have from the left, it's going to be this, and then from the right, it's going to be that. So it's just going to be 1 over pi a naught cubed. And then since this is a inner product, it's going to be the integral over dr. And dr here is just shorthand notation for dv, right? Okay. And then we're going to have e to the negative r over 2a naught. Sorry. It's going to be e to the r over a naught. I'll write this more bluntly. Complex conjugate times delta of r. And then e to the negative r over a naught. This is just the formula for the inner product of the matrix element of delta r in this basis state. Okay, so complex conjugate is obviously the same because it's a real function. So we can combine these two guys together. And what we get is 1 over pi a naught cubed integral dr. And then we're going to get e to the negative 2 r over a naught times delta of r. Okay, so what is this integral? What does this integral come out to be? Let me change color here. This is going to be equal to, okay, well, let's see. If you remember the properties of a delta function, you remember a delta function, if we graph it, it would just be 0 everywhere, right? Except at the origin where it would be infinite, right? Except that the origin is infinite and 0 everywhere else. And this would correspond to delta of x. If we had something like delta of x minus a, it would correspond to a peak at x equals a, right? This is just properties of the delta function. I'm sure you guys remember this. So if we have delta of r vector, this will take the value at r equals 0, okay? So this guy is going to be e to the negative 2 times r equals 0 over a naught, which is just 1. Okay, so basically this whole thing is just 1. So we are left with, oh, I forgot the constants, sorry. Yeah, I forgot the constants. This should be a pi over 2 alpha to the 4th mc squared a naught cubed. Pi over 2 alpha to the 4th mc squared a naught cubed. Yeah, the constants get tricky here. Okay, so you see these a naught cubes cancel out, pi's cancel, so we're just left with alpha to the 4th mc squared over 2, right? And this is the first order energy correction. Pretty easy. You just compute this integral. Okay, awesome. Now let's look at the second part of the problem and see what it says. Okie dokie. So we did this. You can convert it to EV if you want, also plugging in the numbers. But let's look at the next one. Calculate the energy correction for the state n equals 2, L equals 1, M equals 0. While this state is part of a degenerate energy level, the formula for the energy shift can actually be used. Okay, so let's see. In this case, we want to compute the matrix element. So En1, in this case, is just going to be integral dv, and then we're going to have psi, what is it? 210 if I remember correctly. Because n equals 2, L equals 1, and m equals 0. Okay. This, and then delta H, and then psi 2, 1, 0. But if you remember spherical harmonics, so these y, lm, theta, phi, they have the property that y, lm, 0, 0 is always equal to 0. You can look this up. If you Google spherical harmonics and they list you all these spherical harmonics, if you plug in 0, 0, you'll always get 0. And remember, delta H is proportional to the delta function, right? So this will always pick out the r equals 0 component. So which means r equals 0, theta equals 0, and phi equals 0, right? This is what it means. So when we plug this into that, it will always give you 0. So this whole thing is equivalently 0, except for the ground state, right? Because for the ground state, y-lm is just a constant. In fact, for the ground state, y0, 0 is just 1 over radical 4 pi. So our analysis works, and there is a first order correction. But for these, for any L is greater than 0, En is always going to be 0. En1 is always going to be 0. So that was pretty easy. Okay, so this is just a quick example. I hope you understood it. Let's do some more examples.